Boom. Hello and welcome to Calculus 2, the first lecture of the semester, area between two curves. So in Calc 1 you learned that integrals can be used to compute area under the curve. And if you remember, definite integrals were in charge of doing that. So if you had, say, a triangle like this that cuts through x and y axis, and you want to know the area of that triangle, right? Well, you might know the formula for area of the triangle, but we're not amateur. We don't need that anymore. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So area is clearly 12, right? Half base times height. But there is much nicer way to get that. So this over here is a function. And it's a linear line whose slope is rise 4 and then go to the right 6. So we have negative 2/3, right, as a slope, x, and then the y-intercept is 4. So we immediately see that that line, the function, is negative 2/3. Again, it's negative 4/6, right? And then you reduce that. Y-intercept is 4. So to find the area under the curve, you set up the integral a to b f of x dx. And in the integral like that, f of x is like your height, and dx is the width. So there is a multiplication in between f of x and dx. So this dx is not there for decoration. It's extremely crucial to the problem. And if you remember Riemann sums, the definition of the definite integral, it was the limit as n went to infinity, summation I goes from 1 to n of f of ci delta x. It was ci, f of ci times delta x. Well, this delta x and dx are the same thing. You learned that in differentials somewhere in chapter 3 or 4, whatever. So now when you are looking at this triangle, you have a function, and to find its area, you draw a representative rectangle that has the width of delta x and has the height of f of x. And you see that this dx travels from the y-axis, which is x is 0, to x is 6. So delta x will travel from left to right, right? You can say swipe. And then we have our negative 2/3 x plus 4. You have to put that in parentheses, times delta x. You have to put it in parentheses because it's times delta x, dx. Dx multiplies both terms of this polynomial. So this is how we set up area integrals. It's a very simple idea, right? If you remember from your Calc 1, right, if you have some kind of function there, you cut in those, right, rectangles. Well, each one of these rectangles is that dx, except it's infinitely thin. So the first infinitely thin rectangle is on the y-axis in this case, and the last one is at 6, with all of the ones in between. They're all infinitely thin. So that's why the limits of integration go from 0 to 6, because the first representative dx rectangle is at 0, and the last one is at 6. So 0 to 6, you will have representative rectangles everywhere between those two numbers. And then they go up to f of x times dx. And now it's just integration, right? So copy the constant, and then we have x squared over 2 plus 4x computed from 0 to 6. We use fundamental theorem of calculus to compute this, part 1, which tells us that you plug in 6 to both terms here, and then you plug in, well, we can cancel these 2's. So we have negative 36 over 3 plus 24 plus 0 minus 0. 36 divided by 3 is 12. Negative 12 plus 24 is 12, which is what we got with the formula. Now, that's something that you would say, well, why would I go this crazy way if I can just use formula? Well, first of all, to establish the superiority. Second of all is what happens if it's not a triangle, right? If there is no formula. How about square root of x, x squared e to the x ln x, right? All the other things that we could eventually integrate. So area under the curve is going to be a to b f of x dx. And this is what you learned in Calc 1. And the reason why I repeated all of this is because I have to establish the importance of this dx. It's not there for decoration, and every time you don't write it, you are committing mathematical sacrilege. All right? But we are interested in 2 curves. So if I have situation like this, where I have function f of x and g of x, and I am interested in area between the 2 functions, between a and b. Now, obviously, by knowing how to graph the functions, you will find the intersection, and then you shade the area. I guess everyone is showing up next class with the colored pencils and stuff to make this more pleasant experience. You're interested in this area here. The formula for something like that should be easy to see, I hope, because you see that you have a function f on top, function g on the bottom, and if you are to find integral of just f of x, that would give you everything all the way down to the x-axis. So you would compute all of this area if you just do integral of f of x. If you just do the integral of g of x dx, you would only compute this area here. Right? So what is the area that you need? It's the difference between them, exactly. Because the first integral, integral of f, computes everything from the top, where the f is, all the way to the x-axis, which has what we need and what we don't need. The integral of g computes only what we don't need. So when you subtract them, you get exactly what you need, which is the green stuff. So when you put negative in between, you get the green. Make sense? Hopefully makes sense. It's like eating a banana, right? When you buy a banana, it has a peel on it, right? You don't eat peel. So that's the g of x part, right? Take the peel off, and you're left with banana. So now, starting from this idea that integral of f of x dx minus integral of g of x dx will give us what we need, we use the theorem from Calc 1 where we can combine these. Well, all of these integrals are a to b, right? Because they are definite, right? We're computing areas, and both of them are computed between a and b. The theorem in Calculus 1 says that you can combine this into a single integral, which gives us the formula. So area between 2 curves is given as the integral a to b f of x minus g of x dx. And I'll just write on the side as a note that f of x is on top. Right? So it's always the top minus the bottom. You might want to write that in your notes. Top minus bottom. Hold on, Paul. It's going to be right minus left. We're going to get there. One thing at a time. But yes, we're going to get there. So now we see that we can compute area between two curves using this. And I'm going to ask you to compute area between two curves now. So let's have I'm going to make a problem up, so the numbers are going to be terrible, obviously. Actually, no. We can make it nice. How about find area between y equals negative x squared and y equals negative 4. What is the first order of business? What? Yes, graph. Very good. So the first order of business is to graph this. Good luck. That's pre-calc 1. Let's go. There we go.
Here's something tricky. Now that we're working under the x-axis, when we take the integral to take the area under the curve, isn't it going to be the area between, say, the negative x and the x-axis? Like
We are looking for the difference between two values.
right.
So the difference remains the same whether it's on a positive or negative side. Keep that in mind, right? So we don't have to take in consideration, yes, for the area under the curve, you have to worry about whether the function goes below x-axis. Very good. But for area between two curves, you don't. Because area between two curves is the difference of two functions. Okay?
Treating y equals 4 as our like
Y equals negative 4, yeah.
as our x-axis.
No, we are treating x-axis as x-axis. It's just that you see, the difference between 4 and 6 and the difference between negative 4 and negative 6 is 2. So always positive 2. All right, so integral. What are my limits of integration? Negative 2 and 2, nice. The top function minus the bottom function, dx. So this is negative x plus 4. That's what I said, please pay attention. And we have negative x cubed over 3 plus 4x from negative 2 to positive 2. That's negative 8 thirds plus 8. Now we have 3 minus signs in a row. The minus on the function, the minus on the number. Oh, actually, wait. First we do the positive 2. So plus, there's a minus in the formula and minus in the function. So it's a plus 8 thirds. And then we have the hell. Here we go. Plug in 2. That's negative 8 thirds. Plug in 2. Okay, so now we have minus and minus. Yes, so that's negative 8 thirds. There we go. And then negative and negative make it positive, so plus another 8. There we go. Much better. So that's going to be 16 minus 16 thirds. And that should do it. (32 thirds). Cool? Nice. All right, let's see one more problem. And then we're going to switch. We have till 11. Like, we have nothing going on tonight. Just do math. Y equal square root of x and y equal x. Let's see what you get on this one. Right. y equals x is a 45-degree line. Square root of x is a curve. We are looking at this very small area over here. So what are the limits of integration? Great. Which one is on top? Good. So square root of x minus x dx, which is what? X to the 3 halves divided by 3, put the half up there, minus 2x, no, x squared over 2, computed from 0 to 1. We don't have to worry about 0. So we have 2/3 minus 1/2. The common denominator there is 6, so 4 minus 3, 1/6. It's a very quick problem. Now Ryan wants to know what happens when the functions are sideways. What happens when you, let's say, intersect x equals y squared with y equal x? What happens in that case? Well, exactly. But we also have dy. So when you graph this on the side, you're going to get a picture like this. And yes, one of them is not a function. X equals y squared is not a function. But we can flip the formula. We can make y-axis to be the input and x-axis to be the output. So what I can do is I can write the formula integral c to d of f of y minus g of y, everything dy, which turns the formula 90 degrees, and now you have right minus left, because your representative dy rectangle is now horizontal. So you see that your c and your d are values on the y-axis. The representative rectangle starts at c and goes up to d, filling the space. And it's a right minus left, in our case, x minus x, y minus y squared, in our case. So it's possible to deal with problems like that as well. What happened? Stream died already? Wow. Oh, it's back? Okay, good. Yeah, it looks like it transferred, so we'll see. So if I want to solve the problem above, what I do is I set the two functions equal to each other to find the limits of integration. Now, another thing, guys, that you might miss from before is that when you have formula like this, these limits are x1 and x2. They're x values, because the graph goes like this. So those are A and B. And then you have the area in between. When you have the C and D, f of y dy, then these are your y1 and y2. And the graph looks like this. And this is the area, and this is your y1 is C, and y2 is D. So we're going to use a lot of this, actually. So it's dx or dy, and it's very important because that tells you which line, variable is in charge, which is the independent variable. In our case, what's important to see is that, look at this now. x, 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 x. Y, 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 y. They have to match across the integral. That is very important when you're setting these things up, especially in the next two sections coming up for volumes. So now for my problem above, I have x equals y squared and y equals x. Well, I will write this one as x equals to y because y is the independent variable. And then I set these guys equal together to each other. And here I can find the limits of integration. Here are your C and D, 0 and 1. So you set functions equal to each other, and you get the intersection points between the two. Yes?
Did you have any problem?
What happened?
Did you have any problem?
Because it was obvious before what the limits are. But you will always set, these ones. So the next problem will have to do it, because it won't be obvious, right?
So you could have done it for the ones on top if it wasn't obvious. Correct?
Yes. So over here, for this problem, you set negative x squared equal to negative 4, x squared is equal to 4, x equals plus minus 2, and those are the limits, right? For the one below, square root of x equals x. Square both sides, we get x equal x squared. X squared minus x equals 0. Factor out x, 0 and 1, right? So yes, you can do that every time to find the limits of integration. It was the reason why we didn't. It was because the graphs, but now it wasn't obvious, so I did. Yes.
So you still can't do that with a circle.
True. But we'll deal with the circle in chapter 10, and it's going to be like this. It's going to be easier than all of this together. Circle is going to be a joke in chapter 10. All right, so now we have our area 0 to 1. And it's right minus left. So when you look at your picture, linear is right, and the y square is left. So it's y minus y squared. dy. And it's y squared over 2 minus y cubed over 3 from 0 to 1. Again, same thing as before. Got 1 over 6. Bueno? All right. There's another concept and more of these problems, so we'll do more on Monday 6-2. I'll just end the stream here, and we might have a second part, or maybe, I don't know, maybe not. We'll see.